Here in 7.3, we're going to introduce trigonometric substitution, which is a different type of substitution than we've seen before. One in which we're going to be substituting trig functions in to replace variables. And so to kind of motivate the idea a little bit, let's consider this integral of the form square root of a squared minus x squared. And this kind of has a nice geometric interpretation. It's the integral that would tell us something about the area under the semicircle given by that equation. So if I were to try and say something about the area under this semicircle, I would need to evaluate this integral. Okay, so now this kind of maybe gives us some challenges. For instance, if it were of the form x times the square root of a squared minus x squared, then a normal substitution of the form u equals a squared minus x squared would work fine. The problem is, in this case, if we tried that same substitution here, it wouldn't work because the derivative of a squared minus x squared is negative 2x, which doesn't allow us to completely substitute the x variable. Well, we would have some x's left over. So what we have to consider then instead is replacing a trig substitution. And the reasoning behind it is that a squared minus x squared resembles this identity 1 minus sine squared. Right, because you've got the constant minus some variable squared. So that kind of makes me think for something like this, if I were to get a 1 minus sine squared expression inside the square root, then I could turn that into cosine squared, which would then come out of the square root. So that's the reasoning behind it, is that we can somehow use this trig identity if we were to replace x with a trig function. Now let's see how that would actually simplify here. If I substitute x equals a sine theta in for x here, what would happen? So we'll leave a squared minus a sine theta will replace with x, and then we get something like a squared minus a squared sine squared. Now they both have a factor of a squared, which I can factor out. And then, of course, the square root of a squared will just be a. And the square root of 1 minus sine squared will become cosine squared, right? So 1 minus sine squared becomes cosine squared. So the square root of cosine squared, we can then remove the square root. In this case, I would be a little bit careful there. We would actually have the absolute value, because in this case cosine squared would be positive. So the square root would retain the positive value. But we'll see in a moment that if we're careful about how we define theta, then we don't necessarily need to worry about the absolute values. And the great thing is now also, if I were to integrate this function, it would be much easier than what we started with. Right? In other words, integrating cosine theta is going to be much simpler than integrating the square root of a squared minus x squared. Of course, there's a few more details that we have to go through first. And what we're actually doing here is something called inverse substitution, right? Whereas in the past we would say, okay, we're going to replace some expression with a single variable, but what we're doing now is we're replacing a single variable in our integral with an expression, with a function of theta. Okay, and by doing this, now we're kind of doing it backwards, right? Instead of writing the equation in terms of u, where we're replacing some expression with u, we're replacing the whole variable. So this is sort of an inverted way of doing it. In general, we can make any substitution of the form x equals g of t by using the substitution rule in reverse, and we just have to be careful that what we're substituting is 1-to-1 so that we can do the inverse. And yeah, in general, it'll look something like this, right? Where if I have some function f of x, I replace x with some other function g of t, but I also have to replace dx as well with g prime of t dt. So both of those things are going to be substituted. Okay. And now I can try and integrate with respect to the new variable. Okay. So for us, we're going to be careful about how we define the substitution. When we're replacing theta, we want to make sure that it's defined on an interval where that function is 1-to-1. So for instance, in this case, we would have to make sure that theta is between negative pi over 2 and positive pi over 2. Right, so that sine theta is 1-to-1. And in general here, we'll look at three different types of trig substitutions. One involving integrals that contain the square root of a squared minus x squared. So you've got a constant minus x squared. Those will be the ones that involve sine. And the reason that we use sine is because then we can use the trig identity 1 minus sine squared. If I see a squared plus x squared, then we're going to substitute tangent. And the reasoning there is because I can use the identity 1 plus tan squared, right? Because you got a constant plus x squared. And then the third case is if I have x squared minus a squared, then we're going to substitute secant, because then I can use the identity secant squared minus 1. And again, the idea being that after applying the identity, the square root will then simplify. And notice that we've also kind of specified a certain range for theta in each case that ensures that the function is 1-to-1. Okay, and that'll be important to kind of keep in our mind that by restricting this range for theta, we're allowing ourselves to do the inverse step later on. Okay, so each of these three cases we'll look at with some examples. So let's start with an example that is of this a squared minus x squared form. So remember, the goal here was we're going to substitute x equals a sine theta, where we've restricted theta to be between negative pi over 2 and positive pi over 2, so that we can use the identity 1 minus sine squared equals cosine squared. And in this case, it's 9 minus x squared, so we're going to use 3 squared minus x squared. We're going to use x equal to 3 sine theta. But keep in mind, we also have to substitute dx. So taking the derivative of 3 sine theta, we get 3 cosine theta d theta. Okay, so we have 3 sine theta that's going to go in for x here and here. And then we also have 3 cosine theta d theta is going to go in for dx here. So we're going to replace all three of those things with our substitutions that we've mapped out over here. So we'll have 9 minus, here when I do 3 sine theta squared, that becomes 9 sine squared theta. And then downstairs I'll also have 9 sine squared theta. And then dx becomes 3 cosine theta d theta. Okay. Next thing would be to try and simplify this a little bit so that we can use this identity. what I'll do first is factor out all the constants. I can factor out a 3, a 9, and then also from the square root here I can factor out a 3, because I can factor out a 9 from these two terms, and then the square root of that 9 would be 3. So factoring all that stuff out in front of the integral, we get 1 minus sine squared left inside the square root, sine squared theta downstairs, and then here another cosine theta left upstairs. Okay, so here let's just remind ourselves how this is going to simplify now. Because the square root of 1 minus sine squared becomes square root of cosine squared. And in this case, that just becomes cosine. And here I don't need the absolute values, because on this interval here, from negative pi over 2 to positive pi over 2, cosine theta is positive for these values of theta. So I don't need to worry about absolute values anymore. Okay, so coming back here, we've got, well, all this stuff cancels. The square root of 1 minus sine squared just becomes cosine theta times cosine theta. Okay, now I've got cosine squared over sine squared. And that is really cotangent squared. Okay, so we might want to think for a moment how we can evaluate the integral of cosine squared. I'm sorry, cotangent squared. So maybe off the top of your head you don't remember the antiderivative for cotangent squared, but we can relate it to the antiderivative of cosecant squared. Because remember, we have this identity that 1 plus cotan squared is equal to cosecant squared. Okay. So then this would be the same as cosecant squared minus 1. And now we know that the antiderivative of cosecant squared, if you guys remember, the derivative of cotangent is negative cosecant squared. So this will be negative cotangent. So this will be negative cotangent minus the antiderivative of 1, which is theta. Okay. So let's be careful though, we aren't done, because what we have here is in terms of the variable theta. But the original integral that we started with was with the variable x, so we have to somehow return to that variable. So to do that here, I'm going to draw myself a little triangle over here on the side. This will kind of help me go back to the original variable. Because if I look at our original substitution, we said x equals 3 sine theta. Which means that x over 3 is equal to sine theta. So I can fill in the opposite over hypotenuse side here is x and 3. Using the sine ratio. And then the adjacent side, we can do Pythagorean theorem. Will be 9 minus x squared, square root of 9 minus x squared. Right, because there we know that x squared plus 3, I'll say x squared plus, x squared plus y squared equals 3 squared. So it's solving for y there, that's how we got this. Okay, so so now the question is, what's cotangent theta and what's theta? So, okay, so here we can use this equation here, sine of theta equals x over 3 to get theta equals sine inverse of x over 3. Good, so we got an expression there to insert for theta. And then for cotangent, remember cotangent is the adjacent over the opposite. Right? It's the reciprocal of tangent. So we'll do the square root of 9 minus x squared over x. So this will work out to be negative cotan theta will be negative square root of 9 minus x squared over x minus theta, which is sine inverse of x over 3. Okay, so that last step there is a really important step that we don't want to forget. And in my opinion, it's very helpful to draw this triangle and then use the original substitution to fill in the sides of the triangle to help us do that last step.